Okay, our situation is we know that light is a wave, we can measure its wave properties, but this photoelectric effect tends to make us think that it's also a particle. And it can't be both, at least according to the mechanics that we can experience out here among things that we can actually observe directly. Well, this just means that the world is a little stranger than we think, and that what really goes on is not something that we can understand just by our macroscopic intuition. Okay, so here's another thing that happens. If we do current versus voltage for red light, well, we get the same things. Constant current, threshold voltage drops to 0. If we do it for blue light, we get a current out to threshold voltage, then it drops to 0, but the threshold voltage for the blue light is higher than it is for the red light. This indicates that the electrons that come off of the blue light have enough energy to overcome a greater voltage. They have more voltage, they have more energy than the electrons that are knocked out by the red light. That tells us that if the light is somehow comprised of particles, which we call photons, that the photons of blue light are more energetic than the photons of red light because they give the electrons more in the photoelectric material more energy. Okay? Blue light also has a shorter wavelength. A diffraction grating will spread the blue light out more than the red light. Blue light refracts more than red light due to its shorter wavelength. And we have then a higher threshold voltage for the blue light. The shorter wavelength is then associated with greater photon energy. Okay, and here's kind of a picture of our interaction. When light interacts with electrons, it gives up its energy in discrete amounts, as if it was made of particles. And those amounts depend on the frequency of the radiation of the light. Remember now, the frequency is nothing but the speed of light divided by its wavelength. And wavelength is something we can observe using a diffraction grating, right? So we take the speed of light divided by the wavelength. That gives us the frequency. We multiply that by Planck's constant. That tells us the energy carried by each light particle, by each photon. That's the amount the amount of the discrete energy that light of that frequency is able to give up. Now this is totally inconsistent with wave behavior. It has nothing in common with wave behavior. So we have, again, two completely different kinds of behavior in one phenomenon. Wave behavior and particle behavior. I'll also mention that light, which we know to be a wave, also acts like particles. Can particles act like waves? Well, it turns out they can, and this was predicted by Louis de Broglie back in the 1920s. The idea is we take a beam of electrons and aim them at a diffraction grating. This dotted line here represents the diffraction grating, and we get this interference pattern out here, this wavy interference pattern on a screen, on a photographic plate or whatever we use. Now, for a diffraction grating, I've got parentheses around, quotes around diffraction grating. We can't make a diffraction grating like that. What we have to do, because it turns out that the wavelengths are so tiny, is we have to use atomic distances between our lines of the diffraction grating, meaning that we use crystals. We use very regular crystals and diffract through layers of a crystal in order to get this kind of interference pattern. The relationship between the properties of the electron and the wavelength of the beam is given here. Okay, the wavelength is nothing but Planck's constant divided by the momentum of the particle. Okay, so we have a beam of electrons all moving at velocity v, then they all have momentum m sub e times v, and they'll exhibit a wavelength h over me times v. We can calculate that wavelength, we can observe that wavelength using a diffraction grating, a crystal as a diffraction grating. We can measure the distance between peaks, and we can verify this prediction, and it is extremely well verified.